Okay, in this video, we're going to do the last example, which is a banked curve problem. So if a roadway is banked at a proper angle, a car can round a curve without any assistance from friction between the tires and the road. Find the appropriate banking angle for a 900 kilogram car traveling at 20.5 meters per second in a turn of radius 85.0 meters. So let's go ahead and write down our given information. We know that the mass of the car is equal to 900.0 kilograms. We know that the speed of the car around the curve is 20.5 meters per second. We know that the radius of the curve is 85.0 meters. And we know the acceleration due to gravity is 9.8 meters per second squared, and that's the magnitude, not the direction. Unknown, we want to find the bank curve, the angle of the bank curve. Basic equations, the sum of the forces is equal to ma. We know that the force on the car by the earth is equal to mg. And we don't need friction without assistance from friction, but we do need the center-seeking acceleration, which is negative v squared over r hat. Notice that there's no vector sign on the v. Some of you may have been thinking, hey, I need to put a vector sign there. You don't. It's the speed around the circular path, not the velocity. Okay, so let's go ahead and draw the free body diagram. It's not actually the side view of the car. It's actually the side view of the ramp or the bank curve. Okay, so let's go ahead and draw our free body diagram. Here's the center. I'm going to go ahead and draw my weight, which is going to go down. Now here's the thing. My normal force has to have the same angle, or it has to have a length that helps us out with this. So here's my curve. I'm not really sure what the angle is. This is pretty extreme, I think. Okay, so what I'm going to do is I'm going to go ahead and draw this going up as a dashed line. And I know that when I draw my normal force, okay, along the perpendicular, that this component of the y component of the weight, which is the weight itself, has to be equal to the y component of the normal force, because the y components have to cancel out, because I'm not accelerating vertically. I'm only accelerating horizontally this way. Okay, so that means that my normal force is going to be drawn a little bit differently than we've learned in the past. Before we drew a parallelogram. Well, I'm not going to draw a parallelogram this time because this is my x component of my normal force, and that has to equal the magnitude of the weight in order for my y components to cancel out. So this is my normal force, which is force on car by curve, or by road or ramp, whatever you want to call it. Okay, so now again, this is very similar, if you remember. This is a very similar diagram to the ones that we drew in our inquiry, right? When we had the airplane ride and when we had the Ferris wheel. Okay, so it's very similar. The normal force has to bend in order for the net force. Okay, if I were to add these two together like this, notice that my net force is directed towards the center. And that's really what we want. Okay, let me label this force on car by earth. Okay, so now we're going to go ahead and solve the problem. Instead of me breaking the weight into components like we did for the inclined plane problem, we did that because the acceleration was along the surface of the incline. And so it just made sense for us to break the weight into components instead of breaking the normal force and the friction into components. But here's the difference. Our net force has to be directed towards the center. Okay, so that means that I have to actually break the normal force into components. So that means I need to know what this angle is. Okay, well, I know that this angle here is going to be the this angle here makes a 90-degree angle, right? Okay, and we also know that this angle here is theta, and that means that this angle here is also theta. Okay, theta. So this angle here is theta. Opposite angles of two lines that bisect each other they're equal. I think that's some trig thing. Okay, so this angle also has to be theta. So now let's go ahead and write this out. We have the sum of the forces in X is equal to MAX. And we have the sum of the forces in Y is equal to MAY. Let's go ahead and do the Y direction, or I'm sorry, let's do the X direction, because that's really what I need. I need to know what the angle is, sure. But I think that because this is going to be equal to the center seeking force, I want to start there. So this is the X component of the normal force, and that's going to be opposite over the hypotenuse. So that's going to be sine theta once I get to that point. So I have force on car by curve, and that's a subscript X because it's going in the X direction, and that's equal to MA sub X, which is equal to MA sub C because it's center seeking. It's pointing towards the center. Okay, am I accelerating? Why, yes I am. Newton's first law. Substituting in magnitude and direction, I now have force on car by curve sine theta. This is going in towards the center to the right, so I'm going to use I hat, and that's equal to mv squared over r I hat. Okay, the I hats cancel out. And here's a problem though. I do not have force on car by curve, and I also don't have the angle theta. So that means I have two unknowns. Okay, two unknowns means, that's right, two equations. So that means I need to do the y direction. Okay, so I have force on car by curve, subscript y, vector sign, plus force on car by earth, vector sign, is equal to ma sub y. I'm not accelerating in the y direction because my forces add up to 0. So that means Newton's first law, the net force becomes 0. Be careful. Again, a lot of students want to just automatically substitute in here mv squared over r. You can't do it. You're not traveling in the center seeking direction in the vertical direction. You're only doing that horizontally. Okay, so be careful when doing the summation in two directions. One of them can have the mv squared over r, but the other one cannot. Okay, so let's substitute in for magnitude and direction. This is going to be my y component, which is going to be adjacent over hypotenuse, which is cosine. So this is going to be force on car by curve, cosine theta, and that's j hat, minus mg j hat is equal to 0 Newton j hat. Okay, the j hats cancel out. Adding mg to both sides, I end up with force on car by curve, cosine theta is equal to mg. Okay, I need to get theta by itself. I'm going to show you something. This is a little trick. Sine theta, cosine theta. This is the same, this is the same. If I take this equation and divide by this equation, I can get rid of the normal force, and I can get theta isolated. So let's do that. So we're going to take force on car by curve sine theta equals mv squared over r, and I'm going to divide that whole thing by force on car by curve cosine theta equals mg. Okay, this cancels out, m's cancel out, and what am I left with? What's sine theta over cosine theta? That's right, tangent theta. So tan theta is equal to v squared over rg. And that means that theta is equal to the arctan of v squared over rg. And then all we have to do is substitute in our numbers. So the arctangent of 20.5 meters per second squared divided by 85.0 meters times 9.8 meters per second squared. And I'm going to need another piece of paper. Phooey. Okay, so putting this in my calculator, I'm sorry, you need another piece of paper. Hopefully you wrote a little bit smaller than me. If not, you can always put it on the back. Okay, so I have 20.5 squared, and I'm going to divide that by 85 times 9.8. Don't forget your parentheses in your calculator. Okay, so that gives me, theta is equal to the arctangent of 0.505, 3 sig figs. So now I hit my second tangent, okay? And make sure also that you're in degree mode and not radian mode. If you're taking calculus, you may be in radian mode from some of your calc stuff. Okay, and that gives me an angle of 26.8 degrees. So 26.8 degrees. Okay, so that is the angle that my curve is banked at, 26.8 degrees. Now, I want you to think about this. I'm not sure what the answer is, but think about how you feel going around the curves, bank curves, when you're coming off the highway. And that's usually when you find them, is when you're coming off the highway or you're going at fast speeds and you're coming off. Why do they have the speed limit set so low? Think about this problem when you try to answer that question. Because here we have a speed of 20.5 meters per second to give us an angle of 26.8 degrees in order to have no friction, no rubbing, no static friction necessary. Okay, that means no sliding or skidding. Okay, so think about that when we think about how fast that speed limit is going around the curve. I've also noticed, observation on my point, that when I actually go the speed limit around those bank curves, I don't actually feel myself being pulled outward. Okay, so maybe there's something to that. I also know that if you go too fast and it's rainy, or you go too fast and there's a lot of sand on the ground, that your car will actually start skidding. So that's one of the reasons why we really want to pay attention to those speed limits as we're going around the curves. They're there for a reason, and they're there for our safety. But also, I think there's probably some physics involved in that decision as well. Okay, if you have any questions about your lecture notes, please make sure you post them to Edmodo or you let me know in class.